So my name is Daria Kubyshkina, and I'm a postdoc at Trinity College Dublin. And today I'm going to talk about the atmospheric mass loss mechanisms from low to intermediate mass planets and its potential drivers in the context of the planetary evolution. So first of all, why is it important? From recent observations, we know that the overall population of exoplanets look very different from what we know from the solar systems, and planets in mass range from the Earth to Saturn show very large spread in planetary radii and hence in densities which cannot be explained by the observational uncertainties. This population, highlighted here with a rectangle, consists of two distinct groups. On the left are super-Earth planets, the dense and compact planets that host likely no or only the compact secondary atmosphere. And on the right, sub-Neptune-like planets whose low densities suggest the presence of the extended hydrogen-dominated atmospheres. A few factors are likely to play a role in shaping this population, including the planetary formation mechanisms, or presence of high-altitude hazes or clouds, which can visually inflate the observed radii. But the main forming factor is expected to be the heat hydrodynamic atmospheric mass flows. And the main driving mechanisms of these mass loss is yet, however, debated. There are existing the two most prominent, most popular theories or approaches at the moment. First of which is the atmospheric escape due to the stellar irradiation, where the most popular model is the analytical energy limited approximation, which suppose that the stellar high energy XUV radiation is absorbed by the planetary upper atmosphere, heats it up, and therefore leads to the expansion and the mass loss. And the second is so-called core-powered mass loss, where the atmospheric mass loss is expected to be driven mainly by the own thermal energy of the planet, which is born hot and cools down with time. Both of these approaches allow to reproduce the observed population good enough, and at the moment it's not really possible to distinguish between them from the observations. In this talk, I would like to discuss the relative input, the possible relative input from those two sources or mechanisms for different planets. For that, I show here some atmospheric mass loss rate estimates from the hydrodynamical modeling, where the model is outlined briefly on the left. It is a 1D hydrodynamical model considering pure hydrogen atmosphere exposed to the stellar irradiation with constant heating efficiency. And this model was applied to the wide grid of planets with masses roughly between Earth and Saturn, orbiting different stars in the mass range between 0.4 and 1.3 of the solar mass, at close-in orbits out to the habitable zone and under the different levels of the stellar irradiation. So here in the top panel, I show the resulting atmospheric mass loss rates against the generalized Jeans escape parameter, which is shown here in the plot. It is technically the relation of the gravitational energy of the planet to its thermal energy. And each black dot here corresponds to the specific model planet. One can see that we have two distinct branches in this diagram, where the branch on the left is composed mainly of low mass, hot or very inflated planets, and really strongly depend on the relation between the gravitational and the thermal energy of the planet. And the branch on the right consists mainly of heavier, cooler, or more compact planets. In turn, these escape rates for these two groups depend differently on the amount of the received radiation from the star. So in the bottom panel, I show a relation of escape rates against the XUV flux of the planetary orbit, and one can see that the group on the left show nearly no dependence on the stellar irradiation, while the group on the right depends on it nearly linearly. This could be treated as the escape from the planets on the left hand would be driven mainly by the own thermal energy of the planet, and on the right hand is strongly dependent on the stellar irradiation. To clarify, compare here the results from the Hydra models, yet in black, to the most popular models like core-powered mass loss in magenta, calculated for the same, exactly the same planets. And the energy-limited escape, assuming different effective radii of the XUV absorption in green and blue. And on the first glance, it looks indeed that on the left hand, predictions from the Hydra models consistent with the core-powered mass loss, and on the right hand with the energy-limited approximation. However, the closer consideration reveals that it is kind of the order of magnitude correspondence. If you would like to know more about it, please check out our research note, Kubyshkin and Fossati 2021, and also Krenetol 2021. The takeaway message from here is that the main driving mechanism in terms of evolution for different planets is likely different. And then would be good to account when making a population studies, and also when looking at a specific planet, it would be a good idea to start with defining which escape model would be appropriate. The next question, if the main source stays the same throughout the evolution of the planet. To demonstrate it, I consider here the few evolutionary tracks. So the planetary radii against time for a few model planets, reproducing the Kepler 411d in green, which is the relatively heavy planet, relatively far away from its host star, so experiencing nearly no atmospheric mass loss through lifetime, and is mainly controlled by the thermal evolution of the planet. And a few models reproducing K233b, which is a very young planet located very close into its active host star, whose mass is not, unfortunately, well constrained. But from the size of the planet, it is unlikely to be heavier than the Saturn. Here I consider models of 30, 20, 10, and 7 Earth masses, corresponding to very different amounts of the atmospheric mass loss through the evolution, from nearly none for 30 Earth masses to the atmosphere fully eroded in the first 100 million years for 7 Earth masses. So how do these planets, the circles show the snapshots in time, typically 5, 10, and 100 million years, 1 giga and 5 giga years. Say. So when we look at our mass loss diagram, all the planets will move from left to the right within this diagram. And the most of the changes depend less on the amount of the escape, will happen in the first few tens of million years. However, those planets which are heavier start the evolution already on the right-hand side of this distribution, or in the transition region, and remain there through the lifetime. So technically, it would mean that the stellar irradiation would be relevant for those planets throughout the evolution. The lower mass planets can, however, start on the left hand of this diagram and travel to the right one. So in the first few tens of the million years, the atmospheric mass loss induced by the own thermal energy of the planet gonna be relevant. For the rest of the talk, I would like to focus on planets from the right-hand side, for which the stellar radiation is important. It is known, yep, thank you. It is known that the stellar irradiation or the XUV luminosity of the star is closely connected to its rotational rate. And both rotation and XUV luminosity decline with time. But this evolution does not follow an unique path, as stars are born with different initial rotation rates. I show here the figure from Johnston et al. 2020. And first, let's focus on the top left figure. You can see that all stars start their evolution in the saturation regime, where the XUV luminosity weakly depend on the rotation of the star. But those stars which were born as fast rotators remain in this regime much longer than those which were born as slow rotators, which leads to the large spread of possible XUV luminosity at early ages, between 10 million years and about a gigayear, which uncertainty in the stellar evolution can be relevant, as we have shown before, for at least a large fraction of the observed planets in the observed population. This spread is, however, not the same for stars of different mass and is more pronounced for the heavier stars. However, to check how exactly relevant can it be for the final population of planets, we have modeled the evolution of large bunch of planets orbiting different stars. And here I show the distributions of final atmospheric mass fractions after 10 gigayears of evolution for both planets. For half solar mass star and the solar mass star evolving as fast or slow rotator. We considered planets from 5 on the top to 20 Earth masses on the bottom, starting their evolution with initial atmospheric mass fraction between fractions of percent and 30%. One can see that indeed the uncertainty in the stellar evolution history is more relevant for the heavy star and also only for planets in close-in orbits, where it makes more sense to speak about the border temperature, border equilibrium temperature, rather than the specific distance. And this border value would be around 500 K. For very low mass planets, it's irrelevant as they tend to lose all of their atmospheres within the first hundreds of million years. And also for heavier planets starting their evolution with very compact envelopes, it is less relevant compared to those starting with inflated atmospheres. So to summarize, it is likely that the main driver of the atmospheric mass loss from planets relevant for the population studies is not the same for different planets and can also change throughout the lifetime. And the uncertain history of the stellar XUV will be more relevant for intermediate mass planets orbiting heavy stars and being hotter than 500 K. So here I will stop. Thank you, and I'm happy to take the questions.
Thank you, that was great. We've got one question in the chat at the moment, which is on your slide 4, where would the Earth fall?
Here? Is it the right?
Yeah, slide 4, I think that seems right.
Should I read it in the chat?
The question is, where would the Earth fall on this slide somewhere? I don't know if Eric's still listening, he wants to expand.
Yeah, that was my question, was that was where in that diagram would present-day Earth be? Just I'm trying to get a calibration point to understand what I'm seeing in that diagram.
The Earth would be on the right-hand side of this diagram, at around.
I think we've lost your diagram. I think you stopped screen sharing.
I didn't read the question in the chat. So the Earth would be in this diagram around the green line on the left in this box.
Thank you.